Hi everyone. Today I will talk about deep neural network generalization and fine-tuning for 12-lead ECG classification. What's an ECG? ECG is a non-invasive and cheap and very quick tool to assess information about human cardiac activity. And numerous studies started to use deep learning to detect pathologies classifying 12-lead ECG signals. But why don't these solutions work now? There is two main reasons. The first reason is datasets. Open ECG datasets are quite small in size, not diverse in pathologies, and annotated by small groups of cardiologists. These small group annotations are increasing the risk of poor quality annotation. And the second main reason is models. That models trained on these datasets aren't stable to data source changes. So we decide to address this task and propose a methodology which will improve the quality of heart disease prediction regardless of the dataset, so we can change the test dataset and get high quality and improve classification of more diseases. Because small data sets are not diverse in diseases, and we can classify only widespread ones. And third one, we demonstrate that our methodology can be applicable in the clinical setting, which I think is the more important one. So let's start from data. In our research, we use two main data sets. First one is the PTB-XL, which is a publicly available data set, but it's small in size. And the second one is TIS data set, which is closed. It's our data set, which we collected from multiple hospitals. Let's take a closer look. Here we see that TIS is much larger than PTB-XL, that it's diverse in age, in sex, and also what's important, it annotated by 129 doctors, so we minimize the risk of poor quality of annotation. For our experiments, we chose 7 heart pathologies listed here. And for example, the atrial fibrillation is the most spread around the globe.
I'm sorry, so
yes.
For each of these ECGs that you had in the previous slide, you have one of these labels or maybe none of them because they are healthy?
We have, if it's healthy, we have just norm label, and if there's one of these pathologies, we have these mention labels.
I see. And how many of them are normal? On average, I don't know. All of them are normal or?
No, dataset is imbalance, so we use the balance during the training in loss, so we can compensate. Because healthy people are there are more healthy people than people with pathologies.
Okay, so most of them are healthy.
Yeah.
Also, does each picture have only one label, or they can have?
No, it can have multiple labels, and we don't use pictures for classification. We use the time series of ECG, like numbers. Now let's discuss models. We use 5 different architectures. The DenseNet architecture is the main because it hadn't been used before, and we decided to introduce it to ECG, let's say this way. And other 4 are widely used in ECG analysis. We use 5 different architectures to show that our methodology doesn't depend on architecture of model. So it can be used for architectures you want. And here we can see detailed what's DenseNet. It's mostly consists of CNN layers and usual page norm and ReLU activation. Now let's discuss our experiments. We conducted 2 main and 2 additional experiments. During the main experiment stage, we have 2 of them. The first one is we training binary classifiers on TIS dataset and separately on PTB-XL dataset, and then tested on the TIS dataset. Yeah. Yeah.
So this TIS-DN, what is that?
It's model like TIS, deep neural network. we took the TIS, train a data set, train a binary classifier, and test it on TIS test part. And also we take the PTBXL train part, train the model, and also test it on TIS dataset.
So everything is supervised. It's just you first train on TIS and then you continue training on PTB?
During the first experiment stage, we trained only on TIS separately and on PTBXL. Yeah.
These are these branches?
Yeah. And from the table of results, we can see that, for example, for bradycardy, which is SBRAD, at the bottom, we can see that we reach up to 25% of quality increase from 71 to 96. And for example, for left branch bundle block, we increase for 10%. So we can show that our data set perform good on other data from the other source. And for such pathologies like atrial fibrillation, which is easy to see from the ECG, we increase up to 2%. During the next experiment stage, we took 2 models trained at the first stage and also fine-tuned the model of TIS on PTBXL. So we go further and fine-tuned our model on specific small data set and compare quality on PTBXL dataset. And here we can see that on PTBXL dataset, TIS dataset is stable, it's performed good, but fine-tuning the best among of them. It increased the quality up to 2% compared to TIS and up to 4% compared to PTBXL. So our proposed methodology allow to increase prediction quality for small specific data sets, which is very useful because you can take data from a hospital with their doctor's annotation, use our pre-trained models, and get model for this specific hospital. Then we perform 2 additional experiments. We want to show that TIS dataset, yes, it's large, but there's other characteristics of this dataset that allows our neural networks to generalize. And we take the half of TIS and train one network using half of TIS and then fine-tuning it on PTBXL dataset. And we can still see that the quality of half TIS model is high, and like the previous time, our fine-tuned model is best among them. During the second experiment, we try to show that our methodology can be applicable in clinical setting, and for that reason, we took 500 random samples from PTBXL dataset, gave them to 3 doctors from different hospitals, and they annotate this data. And after that, we just compare our model to these doctor annotations. And as we can see, for 3 pathologies, our model surpasses their annotation. And for others, it shows comparative quality. So our models and our methodology can be used in clinical setting.
So here you trust your original annotations more than the 3 doctors?
I will say yes, because our annotation is made by multiple doctors with more than 10 years experience. So in summary, what we have done, we present the methodology that achieves better abnormality prediction quality regardless of data set. So we can test it on each data set of ECG you want. We demonstrated that training neural network on a variety of data sets and then fine-tuning it on a specific data set is better than just applying it on a specific data set. And we show that we need a large variety data set to enable our models to generalize better. And now I will talk a little bit about our current research directions. Yes, it's good that we can say that this ECG contains, for example, fibrillation, but it will be very helpful for doctors using our method if we also highlight the parts when this pathology is present on the ECG signal. So we try to not only predict, but also show where we find it, or our model find it. Our next research direction is ECG signal delineation or ECG segmentation, when we try to split our signal into its three main parts, like P wave, T wave, and QRS complex. And doctors use this information during their annotation, and it will help us to have better features for our models. And another direction is our upcoming open ECG dataset, which will be quite large. It will be annotated not only for classification tasks, but also for segmentation tasks, and will be annotated by many experienced cardiologists. To summarize our experiments and our methodology, we provide to public two main tools. First one is the ECG Leap, which is the Python library which enables to train models, work with ECG different data sets, download them, and also we present our pre-trained models for everyone who wants. They can use them and train on their specific data set. And the second one is ECG Leap web page, when you can upload your ECG signal and see what our model predicted for you. And that's all. Thank you. If you have questions, I will be happy to answer.
Any questions?
Yeah.
I remember when you talked about the challenges of the work, you mentioned that models were not very robust because some of the applications have been done by different equipment, so they have different attributes. Also wanted to know if you check if like the gender of the patient or the age of the gender is a statistically significant factor, or you only train based on the time series data without including this category data?
For this paper, we used only a time series without additional information, but we go further and use metadata such as age or sex of patients, and we can see that age has an effect, because for children, for example, ECG signals look different. So during our experiments here, we used only adult patients.
Did you use or going to use, for example, UK Biobank data, which with their large longitudinal studies in your data set to train and to make it more, for example, accurate in your results, to have so more accurate results?
We use for training only these two data sets because for ECG analysis, there are not open large data sets for ECG. There are some data sets that only annotated for one pathology, so we can't use it to generalize all pathologies.
You mentioned UK Biobank, which might have more applications, but it's hard to get access to that. You have to apply this through very complicated procedures.
Maybe because of this reason we haven't used it during our research.
I have one question about input representation. You said DenseNet, right?
Yeah.
Is that you're converting this somehow to images?
No, we use 1D DenseNet.
Did you try to use things that are designed for speech?
Yes, we tried a WaveNet, but it doesn't work as good as our models.
It's overfitting, or?
It's not giving these higher results. Maybe it needs a little bit more hyperparameter tuning.
You think that these results are improving a sense? So you compared it to dust hairs,
Mm-hmm.
and the results were similar or sometimes better if you believe the ground annotations.
Mm-hmm.
So what would the doctors say? That would they believe?
There are two groups of doctors. First group don't want to work with artificial intelligence in any of its representation. And the second group of doctors are happy because they think that it will really help them during diagnosing.
Did you check that, for example, it agrees with the majority of the doctors?
Yes, we checked we now use it in multiple hospitals, and we try to understand with which doctors our model agree or disagree. And for most of them who are experienced, more than 10 years, they agree. But with like young specialists, sometimes our models disagree with them.
How about using medical ChatGPT, I mean PALM2, which are used heavily by doctors in diagnosing many diseases, including breast cancer?
I don't think that medical ChatGPT is precise to use nowadays, because it needs more data, and also it needs a specialist to control it outputs, because people like to believe what the internet is said, and it's not publicly safe to use it.
It's heavily used by doctors in diagnosing many diseases.
I don't know.
It will read ECG from now, right?
I think it's only answer like to textual questions.
I had this long idea a long time ago that you probably need to take all ECG, not even label, do not care about labels, right? And do some sort of love to vec type of thing that Facebook used for speech, self-supervised.
We think about it, but we...
that here, and it should work better than the supervised one, but it's more computer intensive.
I think it will work, and maybe in future we will come to it. We have this idea long before, but decide to start from something simple and then use it.
I was wondering, so your methodology is the way you train on this particular different data sets, right? Or the sequence. Why do you think it works better that way? What is special about these data sets or different between them that makes it perform better if you do it in that particular sequence? Are they like really different?
I think because they are diverse, first of all, our data set is collected from different hospitals. Like we have different demographical changes in data, we have different ages, different sex, and also that cardiologists aren't, let's call it this way, from one annotation school. Because in each country, each university has its own way of annotating, and because data set is diverse from the point of view of annotation, it like balancing between poor and good quality of annotation, and it helps.
If you just mix them, it performs worse, as I understand, right? If you just mix these two data sets and train on them, then you get the results are worse than.
If we mix, we will have better results than if we choose data from one source, like this way, opposite.
Okay, let's thank the speaker again.
Thank you.